Hello grade 12s, welcome back to another video lesson. In this video lesson we're specifically just going to go over the corrections for those last few questions that I gave you for homework, which was from question 7 to question 10. So you can already see I've already drawn some of the molecules for you, so you can pause and make sure that yours is correct. And then I'm just going to do some just short detailed descriptions and just to make sure that your answer was what it was supposed to be. Okay, so if we look at both of these molecules, we notice that they are both symmetrical. So I'll write that they are both symmetrical. And if you also look, they have very similar molecular masses, right? You can even see that their shape is quite similar. But we do know that the alcohol, I'm going to put number 2, but we know the alcohol has hydrogen bonds and London forces, whereas in the case of the first one we can just see that it only has London forces. Okay, so obviously then we know that more energy is needed to overcome the forces in number 2 than is needed to overcome the forces in number 1. Okay, so the next one said, here's your structural formulas. So you have to support the answer by drawing the structures. So there they are. So we can clearly see that this would be number 1 and that would be number 2. So I can see that they both have London forces and they both have dipole-dipole forces. Okay, but we can clearly tell that although their intermolecular forces are the same, we can see that 2 has the longer side chain, meaning, longer, not side chain, carbon chain, which means that it has the greater surface area. So that would obviously tell us that there's more energy needed to overcome the strong London forces in this one than there are in that one. So the London forces in this one is stronger than that one because of the carbon chain. Okay, then if we look at number 8, we can see I've drawn in all the structural formulas for you. I noticed that it actually asked you for the IUPAC names as well, so I'll also write that for you. So this one was 3-methylhexane, C was heptane, B here is 2-methylhexane, and this one is 2,2,3 trimethylbutane. Okay, so you can see that clearly there is a differing in side chains here. So it says explain the reasons why the melting points of the isomers differ so much. So one thing that you would have noticed is that you can clearly see that the one that has the highest melting point is D, and the one that has the lowest melting point is between A and B. But if you look, A and B are almost identical, and I hope that you can see exactly why. It's because each one only has one methyl group attached to its chain. Okay, so the position of the methyl group causes the London force to not be exactly the same. So it's slightly weaker in A than you can see it is in B. Okay, and that's the best sort of answer would probably be because, it's somewhere in the middle, which means that it's probably a bit slightly more packed than B, but not that different. Okay, so A and B are close as they only have one methyl group. So we can see that it causes the London forces to not be exactly the same. So not exactly the same because of the position of the methyl. Not exactly the same because of the position. The position. of the methyl group. Okay, then if I look at C, I can clearly see that C has the highest melting point because it has the longest chain. So longest chain, therefore largest surface area available for London forces, therefore more energy needed to overcome those forces. And I can see with D, it has the most side chains, therefore it has the smallest surface area, and therefore it has less energy needed to, well, no, sorry, because if you actually look at it, you'll see that it has the highest melting point, particularly because it is the most compact. And obviously it's the because it's the most compact, then it's the most packed in terms of the crystal lattice. So just be careful here, because obviously we're talking about melting points, so it is slightly different. So C, despite having the longest chain and the biggest molecule for surface area, it will need more energy to overcome and has the high melting point than both A and B that are branched. Okay, so we can clearly see that it has more surface area than A and B, which makes sense why it would need more energy to overcome those forces. But D is the most branched, but also the most symmetrical. So although it has the most side chains, it is also the most symmetrical. Okay, so that plays an important role here, is because it's the most symmetrical molecules, and therefore it is closely packed crystal lattice. Meaning that stronger IMF is needed to overcome the most symmetrical crystal structure. So more IMF, so stronger IMF for the more closely packed lattice structure. Okay, so remember, it's just slightly a bit different when it comes to something that is closely packed like this, and we're referring particularly to melting point. So therefore it has the most energy needed to overcome. Okay, so that's quite an important thing, is to remember there is a difference. You can't just treat melting point and boiling point as the same. Okay, then number 9 gives you the two compounds. It asks you now for boiling points of the hydrocarbons A and B. So it first says write down the homologous series for which A and B belong to. So we can see that A is for the alkanes, and we can see B is an alkene. Then it says place the compounds in sequence according to decreasing strength of IMF. So I can see that A is going to have the stronger force than B. So it says in sequence according to decreasing strength. So you would start with the highest to the lowest. So if you wrote it as A and then B is also fine. Then it says name the intermolecular force that exists between molecules in these compounds. Okay, they'll share the same, which is London forces. Then it says, well, then explain why A would have the higher boiling point than B. So propane has a larger electron cloud than propene. So therefore stronger temporary dipoles and stronger London forces. Therefore more energy needed to overcome. The intermolecular forces, Therefore, propane has the higher boiling point. Remember, we're not saying, oh, well, the double bond is stronger than the single bond. Remember, it's not about bonds. It's about the structure. So, because there is more bonds within the molecule and less bonds surrounding the molecule in that electron cloud type of structure, we can then conclude then that there is that less, there's the weaker forces. Okay, so just take note of 9.4. Okay, then question 10 gives you alkyl halides. It says the following table is used to compare boiling points of alkyl halides with each other. So then it says write down the formula for 2 alkyl halides that are dangerous according to you and give a reason for your answer. Okay, so you could choose between any two. So the first one would be CH3Cl. It would also be CH3F and CH3Br. Okay, so the reason why is because if all three of them are alkyl halides, so because they have such low boiling points, they would exist as gases at room temperature. Now, just as a general note, that gases they're gases at room temperature, alkyl halides are extremely poisonous when they are in their gaseous form. Okay, and so we didn't choose iodomethane because it's not technically a gas at room temperature, because room temperature sits at around 21 to 25 degrees Celsius, and that's 42 degrees. Okay, so then poisonous. Okay, so inhaling these gases can cause respiratory problems or, even death. So just to note there. So then it says identify the trend in the boiling points, give an explanation of the trend. So we can see that there is an increasing as we are. So if we look at the first table, no, it also was second table, sorry. The second table, we can see that what's changing is that I am adding, what I'm doing is I'm just changing the halogen. Okay, so I can see that the halogen that has the higher number of electrons has the higher boiling point. So I'm going to say the halogen with the higher number of electrons has the higher boiling point, and you can also say the one that has the lowest number of electrons has the lowest boiling point. So the reason why is because as we go down the table, right, iodine has a lot more electrons than fluorine will, and so that increasing in electrons makes the molecules larger. So as alkyl halides become larger, the molecular mass increases, so therefore the London forces become stronger, and therefore more energy needed to overcome these London forces. Okay, then 10.3 says describe the relationship between the number of chlorine atoms and the boiling point as presented in table 1. Name the variable that must be kept controlled. So I can see that I'm just increasing the number of chlorine atoms in each compound, so, and that's going to increase the boiling point. So it says describe the relationship. So a relationship is either directly or indirectly proportional. So we can see that the boiling point of an alkyl halide is directly proportional. Sorry, I don't know why pen's glitching out. Of an alkyl halide is directly proportional to the number of halogen atoms. Okay, so the constant will be the number of carbon atoms, because that's what's I kept the same, number of carbon atoms, and we also kept the type of halogen, so you can mention both of them. Even if you only mention one, it's fine. Just maybe make a note of the other one so that you also have a second answer for this type of question. Okay. Okay, so that essentially answers all of these questions that we've discussed up to this point. Okay, so moving on, you can write the date, and the heading is now going to be organic reactions. So the second unit, the third unit, sorry, and the last unit in this topic is now involving the organic reactions. Now, the reactions are something that you have to learn off by heart, okay? It's not just something that you can, it's not as easy as the naming and anything like that. Okay, it's something that you have to just keep learning, and if you have a look, you'll see that you would have got the A3 page with a flowchart for these organic reactions. So it should look something like this, where it says a summary of the organic reactions. So when we are done going through all the organic reactions, then we'll be able to see, oh well, we can use this table in order to help us to answer the questions. Okay, so you can, so the date will be the 12th of May. Okay, so if we think about organic reactions, right, there are many different types of organic reactions. So the first type of reaction that we can look at is called a combustion reaction. Okay, that's something that you should be quite familiar with because we do it quite often, especially in earlier grades. So we'll start with a combustion reaction. Okay, so some points to make on combustion reaction is that first of all, it is an exothermic reaction, as I'm sure would make sense to you, right? Because it obviously has to release energy in the form of burning. Okay, so you must be able to write out a balanced equation to represent combustions of alkanes, alkenes, and alcohols with oxygen. Okay, so the general equation is that whatever fuel you have that you are burning, so we'll say fuel and that fuel can be an alkane, an alkene, sorry, let me just see, I don't know why the pen is still glitching out. So The fuel can be an alcohol, it can be an alkane, or it can be an alkene. So we'll have alkane, alkene, and alcohol, which can combust with oxygen, and it will always form water and carbon dioxide. So then you'll obviously just balance it depending on what the substance is that's going through the combustion. Okay, so if we have a look here, the combustion, particularly in this type of reaction, only shows you the substitution reaction. So I'm going to make the substitution one red. Okay, substitution is the category of the reaction. So this particular reaction is a combustion reaction, which is also a substitution reaction, and you can see that CO2 and H2O is always what is going to be produced. So regardless of what reacts, in this case it's an alkane, but it will always form that water and carbon dioxide. Okay, so moving on. So there are two main categories of reactions that we focus on. Okay, well, three being substitution, addition, and elimination. But the first ones that we're going to look at together is going to be the addition versus the elimination. Okay, so if we are moving on here. So I know we did combustion reactions, which is technically a substitution reaction, but it doesn't matter. We're going to just continue. So when we think about an addition reaction, so an addition reaction means that what we are doing is we are essentially going to add something into the equation, into the reaction. So usually when we did addition reactions, we would say, oh, well, they have that general reaction rule which says, well, if you add A to B, then you would get this AB molecule. Okay, so that's just in general how something like that would look. Whereas an elimination reaction is where we would have that compound together and it would essentially react with something else and it would form that A plus that B. So it would kind of decompose into its different substances. And then we said that a substitution reaction is where we kind of replace something. So we would have like AB plus C, which would form like AC plus B. So it's just a way that, so obviously they're not as straightforward and they're not as easy to identify as this, but if we can try and remember this general concept, then it does make identifying the reaction that we're looking at a bit easier. Okay, it's important. You can see that in this flowchart here, there are also a whole lot of conditions that you have to learn as well. So you have to know that hydration requires sulfuric acid, or dehydration would be more concentrated sulfuric acid, and esterification is also concentrated H2SO4, and like halogenation requires sunlight or UV. So these are just things that you have to learn. It's part of the what is required from you, and you can also find it all on the SAGS documents as well, so that you can see, okay, what is it exactly that is needed. Okay, so we've discussed combustion reactions which form CO2 and H2O. Now if we think about the next type of reaction, we've actually already covered it before, and that is the esterification, or the production of esters. So that would be the next type of reaction that we can look at, esterification. So esterification is essentially when we are producing an ester. So if you can remember, an ester is a product of an acid, a carboxylic acid, and an alcohol. Okay, so it's the product of, it's an acidic catalyzed condensation reaction. Okay, so you need an acid to speed up the reaction. In this case, we'd probably use sulfuric acid to speed up the reaction, and we would know that water is always a product that is formed through esterification. So water is always formed. So the reaction takes place between an alcohol, as we already know, and a carboxylic acid. And when they are combined with some sort of catalyst, right? So we would use like concentrated H2SO4. Then that would form the ester plus a water molecule. Okay, because if you think about it, right, there's this OH that has to be removed. So if we look at an alcohol, we would say, well, if we had ethanol, like that, and we have the carboxylic acid, so we would maybe look at propanoic acid. C double bond O, C, C. So you can clearly see that we know that the ester is going to form, but essentially the product of water, it's removing water. So the elimination of water removes the hydroxyl group from the carboxylic acid, and it removes a hydrogen from the alcohol, and together these two H's and the O's form the H2O. That's the byproduct in this reaction. So when you add it together, then it would form that ethyl propanoate, where we would have the ethyl bonded to the propanoate part. Okay, and that's essentially how this is formed. So that's why we said alcohol and carboxylic acid, but this specifically is how the reaction is going to take place. So so if you look, you'll see that it is an elimination reaction, because obviously we are eliminating water in this reaction. So an alcohol becomes an ester through esterification by adding it to a carboxylic acid as well as concentrated H2SO4. Then we have the product of an ester. So we've done two now. We've done the combustion, which is a reaction with oxygen to form CO2 and H2O. And we've done the esterification, which is the alcohol which reacts with a carboxylic acid and concentrated sulfuric acid to get to that ester. Okay, so there's going to be an addition of H2SO4 concentrated, and one thing I also want to mention is that there is also an addition of heat as well. Okay, so we have to add heat also, because remember it's will help to remove that H2O from the solution. Okay, so we can see that the oxygen atom of the alcohol is part of the ester after the esterification. So this oxygen here is going to form part of the ester there. So you can see that the reason why we always said, okay, closest to the single bond oxygen, because technically the single bond oxygen comes from the alcohol. Whereas you can see that the H2O, the double bond comes from the carboxylic acid. And I can see that the H2O is formed from the combination of the hydroxyl group from the carboxylic acid and the remaining hydrogen from the alcohol. Okay, so that's just one of the types of reactions, the two types of reactions that we are going to look at for today. Okay, so we look at combustion reactions, which is I'm going to write it here so that you also know, is a substitution reaction. Okay, so that's quite important. So when you are asked to identify the general reaction, you'll say, oh, it's a substitution reaction. If you're asked for the specific reaction, then you'll say, oh, then it is a combustion reaction. Okay, and if we look at esterification, esterification is specifically a elimination reaction. Okay, because we are eliminating water as part of this reaction. Okay, so your homework then is going to be to complete exercise 41 on page 314. Okay, you can answer the entire thing. It should hopefully not take you too long. Okay, well, now that I'm looking at it, it is quite a it is quite a long one, but yeah, just practice. You can see that some of the first few questions aren't too difficult to answer, they're quite quick. And then, number 6 is just naming, which we've already done, structural formulas, which we've already done. So yeah, just complete the whole thing. It really shouldn't take you too long. The hardest part is obviously just going to be when you have to write the products and things that it's going to form. Okay, so yeah, make sure you go over it and that the exercise 41 is done before you go through the next video lesson. Okay, so just to reiterate, so far with our organic reactions, we've done 2: a combustion reaction, which is a substitution reaction, where we substitute the parts of the alkene or alcohol with oxygen to form H2O and CO2. And then we discussed the 3 general types is addition, elimination, and substitution. So we've done 1 substitution so far, the combustion. And then we've done esterification, which is similar to what we've already covered when we were doing esters, which is a general type of elimination reaction, where we have a concentrated acid, H2SO4, and we also add heat in the reaction in order to form that ester. And also now you can see that it's going to form that H2O product. Okay, so I hope it all makes sense, and good luck, and I'll see you on the next one.